It's 1998, and I certainly don't know what hard work looks like yet. Google is just getting started. I'm not sure Apple's web technology got much better than this. I do think they hit peak marketing here, though. 1998 was also the year Titanic hit the box office, the movie. And here, Leo, 25, is still older than most of his recent girlfriends. It was also the year Tiger gifted us with the Furby, the first successful attempt at an interactive robot pet. Playgrounds all over the world were a frenzy. It was all everyone was talking about in my school. And once the marketing was in full swing, here ensued the Christmas riots of 1998 and 1999. Furby went on to sell 40 million units in 24 languages in the first 3 years alone. And that's impressive even by today's standards, where social media allows marketing, viral marketing, relatively cheap and easy. What I love about this photo, refreshingly, is that there's no smartphones. And there's so much chaos here, it's easy to miss this cheeky chap going for a sneaky self-serve. I also want to know what this guy's vibe is. I mean, being physically restrained in a children's toy shop is an achievement. That's a husband that's been told that if he doesn't bring a Furby home for his kid at Christmas, he's sleeping on the sofa. So thanks for coming, everyone. At this session, I'm going to share my journey reverse engineering the Furby. I hope there'll be something for everybody here. I'll share the setup that I used to explore Furby's capabilities. We'll dip into the original 1990s source code and see what the 90s called a learning machine. And I'll talk about Furby's best-kept secret that enabled it to become the toy of the millennium. My name is Luke McNeice. With a robotics background, I started off at Nortel, developing technology for internet service providers. And as a graduate from university, I joined a fast-growing UK software company, McNeice, and worked on early mobile technology, where I delivered some of the first B2B apps for iPads. It was a lot of fun. Later, I led research and development lab there, and worked on early artificial intelligence, virtual reality, and lots of web and mobile technologies that we now take for granted. Certainly my kids do. And now I lead engineering at a company called Hamilton Robson. We're a mix of software and hardware engineers working with customers like Twitter, X, TikTok, Salesforce, Datadog. And some current enterprise projects that I'm working on is a secure identity and right-to-work checking platform for the UK recruiting platform. A project for the National Archives that secures the environmental effects of all of the assets that they store. And an IoT office space analytics product that helps companies manage their office space that we've built, hardware and software, from the ground up. Some recent more creative projects include digital interactives at a number of science museums all over the world, the Our Place in Space global touring exhibit from the UK children's author, Oliver Jeffers, and an interactive longbow that feels real at the Game of Thrones studio tour. I have a really strong belief that creating opportunities for engineering teams to prioritize quality in structured teams or be creative in flat teams is an effective lever to foster innovation and autonomy to attract great talent. So I'm sure you're wondering how I got here and why am I doing this. But here, for me, actually started in 2014. This is my son, Sam, here, 3. And after a nostalgic car boot sale find, my sister, still traumatized by me continually hiding her Furby, of course, for maximum jump scare effect, brought one home. And naturally, Sam was pretty happy about that. We named him Frank, and it was all going really well until I put batteries in him. There was tears shortly after this. So what is any father to do? So I took a walk to the bottom of the garden, dug up my tools of what I needed, and dissected the little demon. Frank, to be clear, Frank. And for a boy watching this, it worked. Starting off a now long tradition of science lessons at home. And of course, it was only until Furby was in bits on my kitchen table that Sam leaned in and whispered, "You can't talk now, Frank." Wanting to grow that STEM spark, this got me thinking, what would it take to make Furby talk? Of course, Sam wouldn't have the patience for this, and I ended up taking on the project myself. But I actually wasn't a fan of this model. There's something about the eyes. But the original, I think, had potential. Sometimes good and simple eyes are all you need. And with the original Furby having such expressive eyes, if it passed the meme test, it's all good. There are lots more that I could show here. I could only fit a couple on the page. So I got started, and there was a prototype. Then there were lots of prototypes. And with each one, I was trying to figure out how to control individual components to maximize expression, mouth, eyes, trying to integrate them both. But it was all very performance-led. I was kind of a bit lost. And after a year of this, everyone was looking a bit worse for wear. And I was lost. So what is an engineer to do when they're lost? Create a new JavaScript framework, of course, but that wouldn't help here. When I'm lost, I write documentation. And as it often does, it helps me step back and see the bigger picture. Why do we have to do any of this? Was it possible to keep Furby intact? It seemed like such an obvious question now. So there is a handful of people that have been experimenting with Furbies. Some of you might have seen that. And largely is around taking the original Furby and trying to effectively jolt it with electricity to get it to do stuff. Varying degrees. Some of them are a bit weirder than others. These are the PG versions. So let's change it up and have a look at the original source code. So the original source code only leaked on the internet only a handful of years ago. And it was 6502 assembly, which is kind of around the Apple II era, which a lot of people then for a long time thought that it had the Apple II chip inside it. And somehow Tiger managed to get a cheap version of it. Ended up it wasn't actually. It was a kind of cheaper sister, brother of a chip from it. But the assembly is about 197 pages, which actually isn't that much for assembly. And it's very, very well documented. Now, in fairness, the reason why I think it's so small, partially, is because the speech chip, the part that actually made it noises and speech, actually was missing from the leak, at least. It was like a Textus Instruments chip. And if anybody has seen *Halt and Catch Fire*, if you haven't, by the way, it is amazing. And definitely, like as a kind of technical person that loves a little bit of a technical theme, I was able to watch it with my non-technical partner, and in fact, she loved it more than I did. It's a great show. But in the show, this character, Donna, who's kind of introduced as like a technical savant, her story and the products that she works on is actually the first chips that started to create speech synthesis, and it was this product here. That was the same chip that ended up in the Furby. So certainly in the playground at the time when people were having these Furbies, I was a little bit old, slightly a bit too old, I think, at least to not be embarrassed about getting one. People used to name their Furbies, and some people named it what appeared to be some kind of Furby name. Some people just named it whatever they wanted. But the source of truth in the actual source code was that there was about 24 names. And what was really interesting about these names is that they're also actually Furbish. So it was some kind of language that the creative team that kind of created around the product. So names were, for example, very good and like bad and things like that. And nobody really knew that because Tiger hadn't communicated what the Furbish was. They wanted to keep it like a little bit of a creative secret. And it took a long time for that lore to come out. So another really interesting thing that I found in the code was all of the games and the Easter eggs. And certainly in the playground at the time, people used to come in and say, oh, I got my Furby to do this, I got my Furby to do that. And some of the things were like, nah, I've never heard of that. Some of them were quite hard to do. And again, Tiger kept this fairly secret on how to do all of this. You just kind of had to discover it. And I painstakingly went through the source code and extracted out basically all of the things that you needed to do to activate these functions. And just on the key on the right-hand side, light, feed, pet, tickle, noise. So light was basically just cover its eyes. Feed was basically put something in its mouth. Pet basically was like pat it on its back. Tickle was like tickle its stomach. And noise was self-explanatory. And you basically had to kind of do the sequence of things. And you can imagine, like even in modern code, like all of the environmental factors that are going into all these things and trying to figure out in code whether the user's doing these things and what time do you wait until they're stopped and and when do you reset, and lots of really interesting decisions that were made. Two of these stood out to me in the code. The first one was actually Twinkle Twinkle. So I thought this was going to be one of the simpler ones, and it was. But one of the really interesting things at the very end of the program, it put the Furby into a deep sleep. And what I mean by that was that the only way that you could wake the Furby back up again was to hold it perfectly inverted. And then it would just wake up. And I remember going through this, and I was like, what? It's the only one that does this. What is this about? And I remember this lore from all of the parents, and they used to complain that one bug of the Furby was that it didn't have an off switch. The only way you could turn Furby off was to take the battery out. So you can imagine the terrors of parents of kids that had Furbies at night, playing with it. Or sometimes, for example, a light would go off or the curtain would move with the wind and it would wake the Furby up because it would all of a sudden get a strong light. And that did happen. But one of the things I think that Twinkle Twinkle was doing was it allowed parents to take the child to bed, sing Twinkle Twinkle, and leave the Furby with the child with the low risk that they'll be able to figure out how to wake it back up again all night. The other one that stood out to me I thought was quite interesting was Simon Says. So Simon Says is about 25% of the whole program. All of the rest of the stuff is, a couple of paragraphs of assembly, but this thing is pages and pages and pages and pages and pages and pages and pages. And to the point where I got exhausted going through it, but what I could tell was that it was doing an awful lot of hand-holding to figure out what the user was doing and when to speak and when not to speak, and trying to calibrate itself because the motor was quite noisy. So a lot of the trigger points there were from the microphone. But it turned out that the actual Furby itself, as it was doing stuff, was causing this kind of crazy feedback loop. And a lot of the program was actually around trying to defend itself against all these other environmental factors. So a lot of the time, at the time, a lot of the magazine articles, and I'm sure Tiger really promoted this, was that they called the Furby the learning machine. And where that came from was this idea that it could learn English. It started off with these babyish Furby words, and it only ever said babyish Furby words, but as it grew up, it started using English words. And you were encouraged, the lore was that you were encouraged to talk to your Furby and interact with it and teach it these words. And I honestly couldn't find any of that. I mean, that would be super impressive even by today's standards. And this was, back in the late 90s. And what I did find, though, was a bunch of pages and pages and pages of tables. Tables were 100 of the rows in the table was initially Furbish words, and then 90%, and then 80%, and they started introducing these English, basically in these tables. And what I found out when I was kind of going through when these tables were called and when they were changed was that based on how often you interacted, especially Simon Says, with the idea that you're actually teaching in English almost as a fake lore, that it ratcheted it up, its ability to access these kind of progressive tables as it aged. Oh, wrong slide about. I'll do this one first. That was that slide. One of the other interesting things that I came across was when I first started experimenting with these, I just bought 10 of them off eBay, and they were all kind of broken, and I managed to fix some of them. And when I kind of realized that every time you restarted them, they were different. They spoke differently. They seemed to have a personality. And I was trying to figure out how that came about, and it seemed fairly random. It didn't seem preset. It wasn't like it just kept rotating through. It was pretty random. So it was something that I was really interested in trying to find, how they did that in the code. And back in the 90s, random numbers were really difficult. I mean, right now, you just call .rand, and it gives you a random number. And if you, for example, were to take all of those numbers and generate 1,000 of them, put them in an Excel spreadsheet, what you're going to see when you graph that is really even distribution. That's what you want. Back in the 90s, that was really difficult. And a lot of the random number generators that were just pseudo-random, and you would see consistent patterns in them, and they would stay away from certain numbers and seem to gravitate towards certain numbers. But Furby's random number generator was really good. And as I was digging in, what I realized it was doing was it was taking all of the sensor values as soon as it booted for the first time. What tilt was it at? How much light was in the room? How much vibration was happening at the time? How much noise was at level at the time? And it was taking all of those sensors input and compressing it into a single number and using that as a random number to start off with. And what then I found next was it started weighting or handicapping all of the future sensor values forever. And for a long time, I was like, why did it do that? And what I realized was happening, the correlation there was that when you reset it, depending on these sensor values, that you either got a Furby that was particularly tired or particularly wired, where when you're playing hide and seek with it, it would either respond really immediately or it would kind of feel a little bit sluggish or appear not to really respond to sound until you were really loud. And this was all just from this mechanism, from this kind of random number generation that kind of latched on, and I thought that was very clever. So one of the other interesting things that I found was, I found a bug. Actually, one of the interesting things was a lot of the comments, it was very well documented, was there was clearly code reviews happening in the comments, which I thought was really interesting. It's not how we do things anymore, obviously. And you could see senior and junior engineers in the code almost writing each other comments about what changes that needed to be made and what changes then were made. And this comment, what I thought was really interesting. And it turns out that Furby Generation 1, absolute 1.0, was shipped with a major bug in the software. And back then, you couldn't update it over the air. It was tough. It was out in the wild. And actually, because of this, if you find a Furby with this bug, it's actually quite valuable. It's difficult to tell. You need to open it up to tell. But basically, what the bug was, if you didn't play with Furby, it got sick. And the only way to get Furby to not be sick was to interact with it, to feed it, to play with it, those kind of things. But the sicker that it got, the more it didn't want to play with you, the more it didn't want to eat. You can see the challenge here. And eventually it ended up coming down and down and down and couldn't escape from this rut. And this bug that's documented here basically was a patch to not let it get too sick, because the only way to fix it is to fully reset it, and you can lose its personality. I thought that was interesting. So let's talk about some of the experimental setups that I've had. So I've had a few different versions, and I'm not going to go through this in a lot of huge amount of detail, but I would put the build into two categories. One is like a retrofit build, which is taking Furby as fairly intact as possible and just trying to push it around to do things. And I had a couple of versions of those. It's real. It works, but I just wasn't satisfied with those. And a lot of the YouTube, there are some really good ones that are performance, what I would call performance builds, but a lot of the stuff you would find on YouTube, yes, are getting the kind of Furby to move and do things, but it's kind of quite limited in terms of what it can do next or what it can do at the time, or and it's quite noisy and things like that. So I really love the teensies. Is there any microcontroller developers here? So Arduino, for example, is a really accessible way of getting into microcontrollers, which is little tiny chip computers. And you can make lights go, you can make cat flaps alarm, you can build IoT, real physical things in the world. And personally, I really love the microcontroller called the Teensy. It does support Arduino, so it's an easy step up, but it's also, the reason why I have it is because it's blazing fast. When you write like modern OOP languages, you don't really, unless you're at scale, you don't massively need to worry about line-by-line performance. How much memory am I using right now? And a lot of the microcontrollers, they have so little memory, every single line of code, that you have to keep a kind of clock of that in your head. And Teensy basically just makes me really lazy, that I don't have to worry about all of that, and I can just kind of keep going and don't really worry about licking too much memory. Or it's also multi-threaded, which is quite unusual for a microcontroller. And if anyone's done any multi-threaded object-oriented languages, microcontrollers are worse. So I'll talk a bit about that shortly. 3D printing, of course, fantastic. Don't need to speak about that. It's kind of well known now. And a lot of the programming is in C++. So this was one of the first models that I came up with. I called it the V2, and basically was just a chassis. So the ability was a 3D printed motor, and it kind of was geared into the original Furby gearbox. And it was pretty good, but it was pretty noisy, and it was really heavy, and it only, of course, could only do the original Furby motion, and that is, and I'll talk about that in a minute, where it can only do certain things previously and next and stuff like that. So I still wasn't satisfied at this point on my understanding how Tiger managed to pull this off. And this is a really great graph. Like, how did they do this? The Sony dog came out the same year. Yes, it had tons and tons of capabilities. I'm being super facetious with these features here. But so did Furby, and it was really engaging. All of these emotional complexities, and they managed it for $30. How did they do it? So this goal of trying to figure this out, I had a bit of a bias. I have worked awful lot in computer vision tracking and things like that, and I thought it must be something to do with how they're tracking the gearbox, or like, I don't really know. So I started digging into that. And if anybody's worked on any tracking, it's got a lot easier recently with some AI tools, but it is still, and I think for a long time, it will be hard. Yeah, and what I mean by tracking, for example, is just taking a random object and get its orientation and its position in space. But obviously, if you make a gearbox or you make something physical, you can put a lot of constraints on that thing, where you can make assumptions about where, less dimensions basically, and where it is. And Furby obviously had to solve this. And as I say, it's still a fairly hard problem. And what I ended up doing to find this was I came across this kind of eBay purchase, almost like endoscope. And you can see the endoscope, the Furby's upside down, the endoscope's almost up its butt. And you can see us looking down. If I go back and try and start the video again, you can see this little spinning wheel just here. And if you look really closely, you can see that it's got a little hole in it. It's moving super, super fast. And basically all this is just a little plastic wheel with a single hole in it, a light on one side, and a sensor on the other. And as the wheel spins around, you get light, dark, light, dark, light, dark, light, dark, and it happens incredibly fast. Actually, something like ridiculous, like 25 microseconds that wheel is spinning past. And for 1998 hardware, that's amazing. And this is all while it's doing speech and counting and Gearbox, and you can imagine some of the programming challenges, doing all of that asynchronously with non-multi-threaded CPUs. But the problem, so what that gave us, this idea that it could spin around, that gave us relative tracking. Which, what do you mean by that? Is it gave us basically the hands of the clock, but we don't actually know where the numbers ever were, because we can't make the assumption that it's 12 up. And that's fine, it's useful, but it's not useful without knowing where 0 is. So how our 3D printer does this, as an example, is when it first boots up, it will drive itself against the wall, bump the wall, detect that, and go, okay, I'm at home, I'm at 0, I'm going to count from now. And I wouldn't advise this, but as an example, to break a 3D printer, wait until it's done that, put your hand in the carriage's way, and it will not print correctly, it will not print in the right place. And that's it, because you've kind of destroyed its memory of where it originally was. Now, this fancier 3D printers detect the clash, of course, and then they can kind of just home again. And Furby does this very similar, and it's basically got a button in the back, and it basically, as it goes round, it basically, a bit like I don't know where the hands of the clock, the numbers of the clock is, and as soon as it hits the button, bang, it knows where the in and the hands of the clock is, and now we know where a 0 is, and we can start counting from now. And the really clever thing about Furby Generation 1 is as it woke up, this classic yawn, and it kind of leaned back, it actually was the process of spinning the gearbox around to try and find the home button while it was doing that. And as soon as it hit, then it and it was really clever the way that they kind of mapped out all of the different expressions just to do even simple engineering phenomena like this. So this was the gearbox when I kind of started taking things apart. And what I could see, that certain things were connected to certain little plastic parts were connected to different parts of the Furby's face. So I kind of mapped that out. You've got the ears at the top, eyes and eyelids, and I had like a very clever mechanism to do both, but sometimes one and sometimes the other, even though it was the same actuator. Mouth, obviously, and hip, which is this kind of rock effect that it had. And I thought it was quite funny that it looked like a little bird skeleton as well when you took it out. When you add all of this together, you can do simple things like get it to blink, get it to waggle its ears, and get it to move its mouth. Nom, nom, nom. But I still wasn't satisfied. Something else was missing. And it turned out when I started taking them apart, Furby only had one motor. That was the trick. That Sonny a dog had 25 motors. That's why it was so expensive. Furby had one. How could it do so much with one motor? It had to be this. This little plastic sandwich. But I couldn't ever imagine it would be anything like this. And the best way to describe what's going on here is you've seen the little actuator parts, so the kind of longer pieces was the parts that you've seen in the previous slide of the skeleton. But what they were connected to, each of them, was a wheel or like a camshaft that was internal. And imagine this little piece had a little tooth on it, and it was inside this groove, and as the wheel spun round, the kind of tooth had to was forced to follow the path of the groove. So each of these wheels encoded, both in time and at 2 axes of motion, a body part. And then imagine that you stack all of these different kind of motion clocks on top of each other, and you run the whole thing at once. This is a super complicated analog, mechanical state machine. So I started off trying to figure out what all of these paths were doing. And I didn't really know where to start, and I ended up taking photos of them and trying to kind of map them out and things like this. But I ended up kind of not, ended up a bit lost.
Hey, Luke, I didn't know there would be so many people here. I'm so embarrassed.
Now, Siobhan, we talked about this. You promised me that you wouldn't interrupt this presentation. You promised me.
Yeah, but I don't get out much.
Okay, I know, and I should let you get out a little bit more. I should.
Uh-huh.
Are you gonna relax and calm down?
Uh-huh.
Okay. Promise. I'm not sure I believe her, to be honest. Okay, so let's get back to the positional systems. So.
Oh, this is my chance. I knew I would be a singer.
Man.
Ba-ba, black sheep. Have you any wool? Yes, sir. Yes, sir. 3 bags full.
You can't take her anywhere. Now, I'm gonna have to do it.
No, Luke, not the dark. I don't like the dark.
Sorry, guys. Sorry.
Well, how come?
Okay, so I tricked you there. So let me talk about this version of Furby and how that trick was done. So this Furby 3, was a performance-focused design. And one of the key things that I did as a result of researching for this was I looked a lot to what Disney were doing. I don't know whether you've seen some of the YouTube videos, but Disney have made some amazingly small, compact, very organic-looking robots recently. And a lot of the way in which that the design philosophies is really about moving the motors away from the thing that you actually think needs to do work, and to basically use cables over pulleys and things like that to do it. And there's a lot of benefits to that, and this seems to be a lesson that's being echoed in a lot of the new humanoid robots that are appearing on YouTube and things as well. And it basically lets you take most of the weight away from your actuators. And it makes a lot of sense, because if you think, for example, that if you have, look at your hand, how many degrees of motion would you want to put in a hand of some kind? And if you add all of the mass for the actuators in the palm, because why not? It means that when you extend your arm, the mechanism itself puts, your distance times your mass on that pivot, and everything becomes more expensive, of course, because all of a sudden you need a 5 times more torquey motor in your shoulder. So if you end up, for example, just putting cables and put like a human body effectively, and drag it all the way up, and then put all of the actuators basically where actually the mass is a benefit, like your hip or your back, where you can then use it to keep yourself stable. And so I think what we're going to see with a lot of the humanoid things is there's going to be a big shift to kind of this cable actuated area. And that's how I ended up designing this version of Furby, and you'll see some of the designs in a second. So in this version, only the faceplate, so basically the eyes and the mouth, are original. Everything else was designed from the ground up. Control teensy again, but this time, and again this was from Disney research and watching people doing some really clever bode and actuator stuff, they always seem to use this module called the Polulu Maestro. And partially the reason why I got one of these to play with, because I was pretty happy with what I was doing. I was using this teensy, it seemed to be working. But when I got this Polulu Maestro, what I realized is all of that kind of multi-threaded asynchronous motion control that I was trying to do, that it was a headache when there was a bug, it was really difficult. It just took all of that away and basically handled all of that for me, and I basically just instructed it to do a bunch of different things in different time frames, and I just worked out what to do at every single time slice and did it. It was really cool. It's not that expensive either. The sound comes from a really simple MP3 trigger module. SparkFun make it, but there's lots on the internet. And most of the game controller stuff that you can probably see now, I had a real remote in my hand earlier. A lot of that's done through a processing IDE. It's like a little application written in Java, and it runs on a Steam Deck that's down here. So this is actually what's underneath, and if she behaves herself, I will show you the creepy real world that's underneath. Looks very different with its skin off, right? And many, many versions went into this. There was a lot of late night headaches to trying to learn all of the different kind of design approaches that cable actuators required. Now, the part that's missing that I maybe didn't tell you is like, what's doing the pulling? And this is a monstrosity, to be honest, and is an ode to technical debt in the mechanical form, but this is just a big stack of servos that are connected to effectively little tubes, little Teflon tubes with a fishing line down the middle of it, like a nylon fishing line. And effectively, there's like an umbilical cord coming from the Furby that pulls effectively everything in its face. And these little triggers, you can see at the back of the Furby, that those are kind of made to help it interface between the fishing wire that's actually inside it that pulls the face feature and the umbilical cord that actually pulls then the thing later on. And the cool thing is you can almost make this as far as, not quite of course, but you can just make this meters and meters and meters long. And it means that you can take a lot of the mass, a lot of the noise, a lot of the annoying things away from your robot, like I was saying earlier. So from a control and coordination perspective, we've got our teensy here again. And its role here is mostly just orchestration. So pushing and pulling things over serial, different aspects of this diagram will be asking the teensy to do something. For example, it coordinates all of the serial connections between both the motion controller, the MP3 module, and this kind of Java application running in Windows. But one of the interesting things that's probably a bit unusual, I thought it was a bit unusual, was this Paludo Maestro controller and how it worked and how it interfaced and what it meant. And one of the things I just wanted to draw attention to was, yes, it did take away all of these headaches, but it had this really, it took a while to wrap my head around it. It is simple in the end, but it's very backwards in terms of like how you script it. They call it Paludo scripting language. And basically, it's a very heap and stack-driven approach where you effectively have to push any operation that you do, whether it's addition or it's moving a servo, you effectively have to push a parameter, onto a global stack and just keep pushing numbers. So say your function that you want to call has 3 parameters, you have to then push number 3, number 2, number 1, and then you call the function, and the function basically goes after your numbers in the stack, destroys them, and then continues operation. And for me, that just broke my brain a few times. And when you want to add numbers together, you have to put them in backwards, and there's certainly all sorts of little weird quirks. In fairness, I think it's worth it. It's really robustly built. I could definitely say it can have some more features and things, but I've nearly killed this thing a few times, and it just gets back up and restarts itself, and happy enough. And also, a lot of the imports and exports are really transparent. It's just like a text file with really obvious and really simple protocols that's been used. And so you can, if you want to, you're a developer, you can automate like the inputs and outputs of those as well. And I actually managed to get Perplexity's Claude to build Paludo scripts, and the first speech sequence is actually based on when it first started talking, is based on a script that Perplexity's Claude built actually for me, and it built it and it was fine. The rest of the stuff I actually used the sequence builder. It was like a visual UI that generates the code. So what's next for Furby? So I find this a lot of fun. It also teaches me a lot about robotics, something I work on in work a little bit, something I would like to get more into. Happy to talk about that at another time. But so I'll continue to work on this, and this version has lots of problems, as a lot of first versions are. I always say that if you're not embarrassed by your first version of something, you've shipped too late. I'm certainly embarrassed about even the third version. But you can see I'm working on a little bit of motion twist and yaw here, and I almost imagined that, maybe Furby could like flap its feet as it tried to move around. So that'd be a bit ridiculous looking and make people laugh. But obviously, like conversational interfaces are starting to come out now. Wouldn't it be great to be able to have a two-way conversation where the latency is very low? And also give it some visual context. Wouldn't it be cool if you could almost leave this in a science museum for kids, and as they approached it, it appeared to engage them, and it knew who was speaking, things like that. And that's the plan. So hopefully with my next version, I would love to be able to put it somewhere and leave it effectively there. And there's a few kind of kids science centers that I would work at my day job with, and they would love to take this. So I'm a little early finishing. I hope you don't mind. It's a warm day. But thank you for your time. Sit bye.